there is a creature that has turned the body of another animal into a vehicle. This isn't a metaphor. It is, quite literally, its only way to survive. Because this creature has to live in two completely different worlds. One is water. The other is dry land, and on its own, it could never travel between them. It goes by a harmless-sounding name, the hairworm or horsehair worm. It begins its life in water. That's where it hatches, and the only place it can ever reproduce. But to grow, it has to spend months inside the body of an insect that lives far from any pond. Between those two worlds lies an impossible obstacle. The worm has no legs to walk, no wings to fly, not even eyes to find its way. If it depended on its own body alone, it would never reach the water again. And yet the problem does have a solution. It's just that the worm isn't the one who makes the journey. Another animal makes it for him. The hairworm never learned to live on land. It found something far more effective, turning another animal into the part of its body it's missing. Over the next few minutes, we're going to watch how it does this, one problem at a time, and each solution is stranger than the last. Let's start by understanding what it's up against. Picture a living thread. As fine as a horse's hair, barely a millimeter or two thick, but long. Far longer than you'd expect. Most measure between 10 and 30 centimeters, and some pass a full meter. When several of them tangle together, they form a knot so impossibly intricate that, centuries ago, people named it after a knot that could never be undone. They called it the Gordian worm. This animal lives in water, but it carries a problem with it from the moment it's born. To grow, water alone isn't enough. It needs something the water can't give it. It needs to get inside the body of a land insect. A cricket. A grasshopper. An animal that walks across dry ground, far from the pond where the worm was born. And there lies the first obstacle. Because between the water and that insect stretches an enormous distance, and the newborn worm is a microscopic larva. It can't chase anything. It can't leave the water on its own. It can do almost nothing at all. So it does the only thing it can. It waits, and it trusts in numbers. A single female lays millions of eggs. In some species, the figure approaches 10 million. She releases them into the water in one long strand, and from them hatch larvae so small they're invisible to the eye. Those larvae drift to the edge. They fasten themselves to the plants along the shoreline, right on the thin border where water meets land. And there they do something remarkable in its simplicity. They seal themselves inside a protective capsule and put their lives on hold. They stop growing. They stop moving. They become a tiny dot stuck to a leaf, waiting. Think about the scale of that gamble. A microscopic being, motionless, at the edge of an enormous pond, waiting for one single stroke of luck, that an insect comes to eat that plant and swallows it by accident. Most never manage it. The vast majority die right there, waiting for an encounter that never comes. That's why there are millions of them. The plan doesn't need every larva to survive. It only needs one. And when an insect finally swallows one of those capsules without noticing, the hairworm has solved its first problem. It has gotten inside. But getting in is only the beginning. Now the hairworm faces a new problem, and a delicate one. It's inside an insect, and it needs to grow in there. A great deal. But if it grows too fast, or takes too much, it will kill its host too soon. And a dead insect on dry land is no use to it. That would mean being stranded halfway. So the hairworm has to do something that seems to contradict the very idea of a parasite. It has to feed on the insect without killing it. And it manages. For weeks, sometimes months, the worm grows inside the insect's body, taking what it needs, little by little, without shutting it down. On the outside, the insect keeps walking, feeding, behaving completely normally. There's no sign of what's happening within. And what's happening within is hard to believe. The worm doesn't grow a little. It grows until it reaches a length 3 or 4 times that of the insect containing it. A body far longer than its host, folded and coiled over and over inside it, until it fills nearly every available space. One researcher described it in a way that helps you picture it. It's like stripping half the weight out of a car and still getting it to start and reach its destination. The insect walks around with half its insides replaced by worm, and it keeps functioning. Notice what the hairworm has solved here. It didn't learn a new way to eat. It found something harder, a way to grow inside another living thing without destroying it, keeping it on its feet for exactly as long as it's needed. Because it's going to need it. Now that it has reached full size, one obstacle remains, the hardest of them all. It has to reach water, and it can't get there on its own. This is the central problem of the whole story, and its solution is what has made this animal famous. The hairworm is ready to reproduce, but for that it needs water, and it's trapped inside a land animal with no reason at all to go near it. Think about the ordinary life of a cricket. A healthy cricket avoids open water. To it, a pond or a stream is a dangerous place, open ground, no cover, where it's exposed to anything that might want to eat it. Its instinct keeps it away from water. Close to the undergrowth, to the shade, to the dry. If the insect behaves like what it is, the worm will never reach water. The entire plan depends on breaking that instinct. And the hairworm breaks it. At some point, once the worm has matured, something in the insect's behavior begins to change. The cricket stops avoiding open spaces, it stops hiding, and it starts to feel drawn to exactly what it used to avoid: the open ground, the shining surfaces. Here is where the detail matters. In a forest, at night, there's one surface that shines more than any other: water reflecting the light of the moon. To an insect whose behavior has been altered, that bright sheet becomes an irresistible signal. It walks toward it, and it ends up in the water, the one place the parasite can complete its cycle, and the most dangerous place for the insect itself. Here we need to be precise, because this part is very often told wrong. The cricket doesn't decide to kill itself. There is no will to die. What the worm does is subtler, and in a way more unsettling. It changes what attracts the insect and what repels it. The cricket still makes its own decisions, moment to moment. But it makes them on the basis of a system that no longer fully serves its own interests. It walks toward danger, convinced, as far as an insect is convinced of anything, that it's doing the right thing. And how does the worm pull this off? This is perhaps the most astonishing part. We still don't fully know. It's been found that the brains of manipulated insects show altered substances, and that the worm seems able to produce molecules very similar to the insect's own, as if it were speaking its same chemical language. But the exact mechanism remains one of biology's great mysteries. And perhaps the most revealing thing is this: when the worm is removed from the insect in the lab, the cricket tends to recover and goes back to behaving almost normally, which means the parasite breaks nothing permanently. It doesn't destroy its host's brain. It only holds it in an altered state for exactly as long as it needs, and then lets it go. What matters isn't the chemistry, it's what the hairworm has achieved. It doesn't need to destroy its host to control it. It only needs to change its behavior just enough to make it carry out, on its own legs, the journey the worm cannot make alone. And when the insect touches the water, that journey is complete. All that's left is to get out. The insect has reached the water. For the hairworm, this is the moment that justifies everything before it. But even now, in the final stretch, one obstacle remains. The worm has to leave the body it grew inside. And it's not a quick exit. A mature hairworm can take several minutes to emerge, an impossibly long body sliding out, little by little, from a much smaller one. Seen from the outside, it's hard to believe all of it was contained inside the insect. Throughout that time, the insect is left defenseless in the water. And here, nature holds one last trap. An insect floating on the surface is an easy meal. Often, at that very moment, a fish or a frog comes along and swallows it whole with the worm inside. For almost any other parasite, this would be the end, ending up in the stomach of the wrong predator, digested along with its host. The hairworm, no. When the predator swallows the insect, the worm is able to escape twice. First, it leaves the insect's body, and then it leaves the very fish or frog that ate it, working its way out. It survives being eaten. It's one of the very few creatures able to come out alive from inside an animal that has just swallowed it and carry on as if nothing had happened. And once free in the water, the hairworm reaches its goal at last. It finds others of its kind. And here appears one of the strangest images in the whole story. Males and females tangle together, many at once, forming a mass of bodies that slowly writhes over itself. So many worms interwoven that they stop looking like individual animals and become a single living knot. It's that very image that, centuries ago, gave the animal its name. The Gordian knot, the knot that could not be undone. The name this story began with describes, in truth, its final act. From that tangle come the eggs, millions, once again, released into the water in one long strand. And on the bottom waits a new generation of microscopic larvae about to face the same impossible plan from the very first step. The cycle has closed. Against all odds, the hairworm has done it again. But one last question remains, and it's the most unexpected of all. We've followed the whole plan, getting inside another body, growing within it without destroying it, changing its behavior to reach water, getting out, surviving, even being eaten, and reproducing. A plan with far too many points where everything should fail, and which nonetheless has been working for more than 100 million years. We could end here, but there's one final piece, and it changes the scale of the entire story. Until now, we've looked at the hairworm up close. One worm, one insect, one pond. Now we're going to pull back, far back, until we can see the whole forest. For that, we have to go to a specific place, a mountain stream in a forest in Japan. There, researchers spent years studying what the river trout ate, a threatened species living in those cold waters. They wanted to understand where their food came from, and they found something they didn't expect. Much of what those trout ate didn't come from the water. It came from the land. They were land insects, crickets, grasshoppers that one way or another ended up falling into the river and being eaten. The question was why? A healthy cricket doesn't go near water. Why were they falling into the river in numbers large enough to feed an entire population of fish? The answer was the hairworm. Insects infected by the worm were 20 times more likely to end up in the water than healthy ones. And adding up all those insects driven into the river by the parasite, the scientists calculated something astonishing. They came to make up around 60% of all the energy those trout consume in a year. Sit with that figure. More than half the food of an entire population of fish depended, in the end, on a microscopic worm altering the behavior of the insects that fall into the water. And the effect doesn't stop at the trout. When that food falling from the forest is plentiful, the fish stop searching as much for food on the riverbed. The small invertebrates living among the stones are left in peace. That affects the algae those invertebrates feed on. And so the change spreads, step by step, through the entire ecosystem of the stream. A single parasite, solving the problem of its own reproduction, ends up moving the energy of an entire forest toward the water, and rearranging who eats whom across a whole river. Sit for a moment with what that means. A worm with no eyes, no brain, no legs, solved a problem that seemed impossible: how to cross from one world to another when you cannot move. It solved it by turning another animal into the part of itself it was missing. And in doing so, without ever intending to, it became one of the pieces that keep everything around it alive. The next time you see a cricket crossing the ground, remember that it might not be alone, and that what it carries inside may be connected by invisible threads to the life of an entire river. You were just looking at it from too far away.